So for this exercise, let a0 be 1. For n greater than 0, an is 1 over 4 of 2 times an minus 1 plus 3. We need to use induction to prove two statements. The first one is for all natural number n, an greater than or equal to 1, less than or equal to 3 over 2. And the second one is an less than or equal to an plus 1. So in fact, we are proving that the sequence an is increasing and it's bounded from below by 1. It's bounded from above by 3 over 2. Okay, so for the first step, we need to prove two inequalities. The first inequality is an greater than 1 for all natural number n. We do it by induction as follows. We need to show that for all natural number n, an greater than or equal to 1. The base case is n equal to 0 because we need to show it for all n in n. So n equal to 0. A0 is 1 by definition. And 1 greater than 1. So A0 greater than 1. So base case is true. For inductive step, let n be a natural number. We suppose that an greater than or equal to 1. This is the inductive hypothesis. We need to show that an plus 1 greater than or equal to 1 too. So this is P of n is true. We need to show that P of n plus 1 is also true. So by definition, an plus 1 is given by 1 over 4 times 2 an plus 3. So this equal to 1 over 2 an plus 3 over 4, right? So distributive. By inductive hypothesis, an greater than or equal to 1. So this number greater than 1 over 2 times 1 plus 3 over 4. And this bigger than or equal to 1. Therefore, an plus 1 bigger than or equal to 1. And therefore, we prove that P of n plus 1 is true. By principle of mathematical induction, we prove that for all natural number n, an greater than or equal to 1. So we did that. So the second inequality we need to show is that an less than or equal to 3 over 4. Sorry, an less than or equal to 3 over 2 for all natural number n. Similarly, base case n equal to 0, we have a0 equal to 1 less than or equal to 3 over 2. This is true. Inductive step, we need to show that for all natural number n, so let n be a natural number. Suppose that it is true for n, so an less than or equal to 3 over 2. So this is P of n is true. Suppose P of n is true. We need to show that P of n plus 1 is also true. So we need to show that an plus 1 less than or equal to 3 over 2. By definition, an plus 1 is given by this formula. By distributive, we have is equal to 1 over 2 an plus 3 over 4. So recall that by inductive hypothesis, an less than or equal to 3 over 2. So an less than 3 over 2. So we have this less than 1 over 2 times 3 over 2 plus 3 over 4. So this is 3 over 4 plus 3 over 4, which is 3 over 2. Therefore, we prove that an plus 1 less than 3 over 2. So we prove that P of n plus 1 is true. Therefore, by induction, we did prove that for all natural number n, an less than or equal to 3 over 2. So we are done with the part A. For the part B, we need to show that for all natural number n, an less than or equal to an plus 1. Base case is P of 0, a0 less than or equal to a of 1, right? So a of 0 by definition is 1. A of 1 is given by the formula 1 over 4, 2a0 plus 3. And we just replace a0 equal to 1. We can compute a of 1 is 5 over 4, which is greater than 1. And therefore, P of 0 is true, meaning that therefore a1, a sub 1 bigger than a sub 0. Inductive step, let n be a natural number. Suppose that P of n is true, meaning that an less than or equal to an plus 1. We need to show that P of n plus 1 is true, meaning that we need to show a sub n plus 1 less than or equal to a sub n plus 2. By definition, a sub n plus 2 is given by this formula. So 1 over 4 times 2 a sub n plus 2 minus 1, so 2an plus 1 plus 3, n equal to this by distributive. Now recall that we did show that an less than equal to 3 over 2 for all natural number n. In particular, it is true for n plus 1. So an plus 1 is less than or equal to 3 over 2. So we can use that right here. So 3 over 4 we can rewrite as 1 over 2 times 3 over 2. 3 over 2 is bigger than or equal to an plus 1. So therefore, this number is bigger than this one plus 1 over 2 times an plus 1. Just replace this one bigger than this one. And this an plus 1. Therefore, an plus 2 is bigger than an plus 1. So by induction, we prove the statement that an plus 1 greater than or an for all natural number n.